I hope my screen is visible to you. So in this session, we cover automatic or recursive function, and then um, we will go forward. So just recall, we had discussed automatic or recursive function. We had also discussed task also in the form of automatic task or reentrant task. This is recursive function, that is recursive function and automatic function both mean same. Automatic task and reentrant task both are same. Okay, so let us understand what is the meaning of recursive. So recursive function is a function calling itself, a function being calling itself, that is called recursion or recursive. So here we understood that if a function is called concurrently from two locations, the results are non-deterministic because both calls operate on the same variable. Hence, we were using automatic or in the just below the function, function name. Then by doing this, we were declaring the function to act as a recursive function, where the function declarations are allowed dynamically. So this is what we observed, and we were, just took one example to understand it. So also I was writing some example of the factorial. So to avoid confusion, I have taken have typed it and kept it in front of you. Just have a check. Module definition and register declaration, all those things, calling of the function, all these things we can do it. There is no logic there. The logic is hidden in this particular function. So I'm highlighting only this. Let us take this code into the Xilinx and we shall verify the same. Please concentrate for this thing, or else it's difficult to understand. And this recursive function also comes in C program also. In C program also we have used it. Let us go through it. Function automatic, just will be, after the function I'm using automatic. Declare the range or the data type. So I'm declaring the range. It's been 32-bit. Factorial is a function name. Means whenever we declare a function with a function name, in the backside, in the backdrop, there will be a register declared with this name factorial of the same vector size, that is 32-bit. 32-bit, it's as good as declaring reg 31 down to 0 factorial. It is as good as declaring that. Okay, so it will happen, two things happens here. One is function is declared and followed by register of the same function name with the same vector data width is declared. Okay, next, input. What are the input arguments it can receive? So input arguments is a 32-bit again. So we are naming it as n. Means whenever this function is called, we call it like this. Factorial. Input argument will give some number. This number will be of 32 bits. So this is the meaning. Okay. So this number and n is mapped. Whatever I pass it here in my main module, there will be something which is declared as number. I'll be giving some number to it, and that number will be mapped to this n. That's the meaning. Okay. Now with this n, whatever I receive from the Verilog module, let us see what we can do. So what I'm doing is I'm just comparing it with 2. If it is greater than or equal to 2, then this particular thing gets executed. Else, the next thing will get executed. What's the meaning? Let us take that it is false. Means n is equal to 1. If n is equal to 1, what is a factorial? Factorial is equal to 1. Let me check. If n is equal to 1, the factorial is equal to 1 itself. So just here, when the function is called, n is passed to be 1, number is 1, thus 1 is mapped to n is equal to 1, it will come over here, 1 is greater than or equal to 2. No, it is false. Hence, else part gets executed. Factorial is returned as 1. So this function will return the value of the output as 1. So 1 is a factorial output. Now think that n is equal to 2. Now when n is equal to 2, so 2 is greater than or equal to 2. So this will be true case. So in this case, what happens is factorial is equal to factorial n minus 1. What is n minus 1? 2 minus 1. Let us see here. If n is equal to 2, this executes. So this statement here, what happens? I just write fact, okay? Factorial means factorial. So factorial of n minus 1 means 2 minus 1 into n. So what is the meaning of this? Factorial 1 multiplied by n. Yeah, so this n is 2, right? I'll write it here, 2. So now just check. Factorial of 1 means what? So it is like calling factorial of 1 means you are calling the same function. That's why it is called as a recursive function. What is the input argument? Input argument is 1 now. So n is mapped with 1. So it will come over here. 1 means it will execute the else part. Factorial is returned as 1. So this recursive function, this will return as 1. This will return the value 1 into 2, which is the value equal to 2. Now similarly, I take n equal to 3 for explanation. Just check. N equal to 3 means this will execute. So factorial is equal to factorial of 3. N is equal to 3, right? 3 minus 1 means 2 into n, in place of n it is 3. So factorial 2 means what happens? Factorial 2 means already we have shown here. Factorial 2 means, so same thing happens. It's like it is calling this function again, this function again. So when this function is called again, so see, when n is equal to 2 means factorial of 2 is invoked. N equal to 3 means factorial of 3 is invoked. So factorial of 2 means it returns 2. I know it. I could have written 2. But to elaborate, I'll just go through it. So what happens here in whenever factorial 2 is called, this particular statement comes, or this particular statement comes. Fact of 1 into 2. So this is what this statement I replaced with this, and this is as it is. So what is fact of 1? Factorial of 1. Factorial of 1 is already 1, that we have discussed. 1 into 2 into 3, which is equal to 6. So similarly, the last explanation I take for n equal to 4, which means you should invoke it at fact of 4. When fact of 4 is invoked, it will execute this particular statement. So fact is equal to fact of 4 minus 1 is 3 into 4. So fact of 3 means what? Fact of 3 is already, we know that it is 6, right? I'll just elaborate it. So fact of 3 means it is fact of 3 minus 1, that is 2 into 3. That's the meaning, into 4. Now, what is fact of 2? Fact of 2 means already we have written here. So fact of 2 means I use a flower bracket. Fact of 1 into 2, flower bracket closed, and into 3 into 4. So this is equal to, what is fact of 1? Fact of 1 is 1. Fact of 1 is 1. 1 into 2 into 3 into 4. So this will be 4 3s are 12, 12 2s are 24. This is how the factorial is computed. This is called recursive function. So whenever you use recursive function, very important point to remember. So whenever you use a recursive function, make sure that there is an exit condition. There is an exit condition. See, when you use a recursive function, think that you have not written this. This thing is not there. Then it will go on calling the function within the function. It will enter the infinite loop. Somewhere it has to stop, right? That stopping, that exit condition we have mentioned here. That is like when n reaches less than 2, then else part gets executed. So finally, it is not calling the function again here. This particular part is not calling the function again. Rather, it is returning some fixed value. So when it returns, so it means this function is going to end at some other point when that particular condition satisfied. So it is not entering the infinite loop. And you should be very careful, while putting the conditions and all. Make sure that this condition, that exit condition occurs, or else it will enter the infinite loop. This is called the recursive function. Very important. Very important. Okay. So now let us take it in the Xilinx and check whether it works according to our wish. Same code, okay? I have already written here. Yeah, check here. Function automatic 31 down to 0 factorial. Input is 31 down to 0 n. So begin. So if n is greater than or equal to 2, so factorial is equal to factorial n minus 1 into n, else factorial equal to 1 and end function. So end model. So here these things I have, to just reduce my writing effort, I have just, I mean, in simulation I need to go on entering the constant. So to avoid it, I have just used it. So initially I force n equal to 3. Let me take it as 5. So 3, 4, 5, and 10. So let us execute it. So for n equal to 3, so the n, so here, how the function is called in the Verilog modules here. Display factorial of n is equal to percentage d is percentage d, means factorial of n is equal to n is equal to 3. 3 gets displayed here. Is percentage d. In this place, the return value of the factorial of n gets displayed. So factorial of n also returns the 32-bit vector. So that is what I am displaying here. So for n equal to 3, value will be displayed. For n equal to 4, output value of the factorial will be displayed. 5 also, 10 also. So that is what we check now. So I'll simulate it. So this is how the invoking of the function is done. Factorial n means this n value is 3, right? With n equal to 3, so that will be mapped with this small n. Capital N is mapped with small n. So that n equal to 3 will be passed to the function and then it will generate the factorial output. So don't look at here because we are already writing the stimulus block. Look at here. Look at here. So factorial of n is equal to 3. So here, factorial of n is equal to 3 means how much? 3 into 2 into 1 is 6. Factorial of n equal to 4. 4 3s are 12, 12 2s are 24, 24 1s are 24. So factorial of 5, like 24 is already there, 24 into 5. So you will get 120. So factorial of 10, so you can do it, so you will get this value. So this recursion function is exactly working according to our wish. So this is the way of writing recursion function. So while writing a recursive function, the important point is mention the exit condition. If you don't mention the exit condition, then it is a blunder. It enters the infinite loop. So it's a blunder, okay? So think that in your exam, if this question is asked, and if you don't mention the exit condition, then we feel that the evaluator will feel that you have not understood the concept of recursion itself because you don't know how to put the exit condition. So it is very important. Is that clear? I hope the things are clear now. So let me check if you have any doubts. If you have any doubts, please come up in the chat box. Next, we shall proceed. Next, constant function. There are two additional features provided in the functions. Constant function, just understand it conceptually. Let us not dig much into the deep. So these functions can be used instead of constants. It's just simple. Then we are comfortable using constant itself. If that is the case, then go ahead with using that constant itself. But this provides an additional feature. That additional feature, let us understand. Okay. The example shows how the constant function can be used to compute the width of the address bus. Let us just check the address. Here is a code. I hope the font is clear. Hope it is visible. Module RAM. So we are constructing a random access memory model wherein I have used a parameter called RAM underscore depth equal to 256. Means wherever RAM underscore depth appears, it will be replaced with 256. Now here we have a function called CLOGB, just some random name, CLOGB. So what this is doing is, this is a function, okay? This is a function. This is a function call. So in this function call, this is a function name followed by, this is an input argument. What is the input argument? RAM underscore depth, that is 256 is an input argument. So whenever this encounters, actually here it should be a constant, right? Some constant I want here. Input means some value I wanted to have here. So that value gets computed by the function like here. So this will call this constant function. So function integer CLOGB. Integer is just it's a data type. So CLOB2. So we are declaring this is also an option, or else you can just put a semicolon, write input here separately. You can write input is integer depth. You can also write it here. Okay, I'm telling it. Input is of type integer depth. Okay, integer means, see, wherever integer comes, you just imagine that it is 32-bit. It's system dependent in most of the case, normally 32-bit. So what is happening here? For, so there will be a register created by this name CLOG clock B2, I can say. So that we'll initialize it to 0. Depth. So this depth gets mapped with what? This input argument. The input argument is RAM depth, which is now 256. That 256 will be assigned to depth, so that will come over here. 256 greater than 0. Yeah, of course, yes, of course. So this is a increment. Every for loop it gets increment. Depth is equal to depth greater than depth shift. It is like right shift by 1. So shift by 1. So here what is happening is, so depth is 256, right? This is 256. So 256 means it is as good as, let me write it here. Uh, 2 raised to 0 means 1, 2 raised to 1 means 2, 2 raised to 3 means 8, 4. 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 16, 32, after that 64, after that 128, after that 256, means 1, 0, 0, 0, 0, 0, 0, 0. It means depth is nothing but, for example, I want to have a memory. I want to have a memory which is having a depth of 256. If I call it as one location, how many locations I'm having? This is 1, this is 2, this is 3. Like that, I'm having 256. 256 total locations. Total is 256. To have this much locations, how many address bit I need? That is what gets decided here. How many address bit is needed? We can easily analyze, like 2 raised to 0, 2 raised to 1, 2 raised to 2, 3, 4, 5, 6, 7, 8. If we need 8 bits, we can directly find it orally. But for writing a program, if I want to write a program for it, this is the method. See what we are doing. So first condition, it gets satisfied. Depth is greater than, of course, greater than. So what we are doing here, it is a right shift. It is a right shift. Shift it by one time, so you'll get it as 1 0 0 0 0 0 0. So now this is my new value. Depth value is this one. Now depth value is 128. 128 is still greater than 0. So again right shift happens. Again right shift happens. So this one comes over here. Means previous allocations will be filled with 0. Okay, that is understood. 0 0 0 0 0. Now it is 64. Again right shift. So like that it goes on shifting. How many times? So it will reach here. I'll show it once again. So one more time shift. One more time shift. Next. Again. Again. So how many times shifting happened? 1, 2, 3, 4, 5, 6, 7, 8 times shifting happened. Now 8 time is shifted. Now 8 time is shifted. Now what happens when I shift it? When I shift it, it is 0. Now you come here. Depth is equal to 0 greater than 0. It will not execute. Hence, no more shifting happens after 8. So here, after it shifts, depth is equal to 0. So when 0 is greater than 0, so no, it will not execute. No more shifting happens. So hence, it will decide that it needs 8 bit of address bit. 8 bit addresses. 8 bit address vector. That is needed. So automatically you need to compute it, right? Whenever you need 256 bit, you need to compare it with 2 equal to 2 raised to n. So then n will give you 8. So this particular thing we designed a logic. You can give 1024 that will return around 10 bits or 11 bits, whatever it is. Okay. So this is how the computation or constant functions are used. So here the constant will be written. What is that constant? Constant will be written. So one time, two time, three time, four time, five, six, seven, eight, 8 times it will shift. So hence 8 will be written here. 8, there is a minus 1 here. So 8 minus 1 means 7. 7 down to 0. It is as good as writing input 7 down to 0. So this 7 we got it from actually 8 because here it is minus 1, right? This 8 we got it from this function. 8 minus 1 is 7. Okay. So this is the concept of the constant function. Next we shall understand signed function. Signed function allows the signed operations to be performed on the function written values. So signed operations like it will take care of the sign bit. Let us look into the example. So here I am having an example of module top. So this returns a 64-bit sign value. Just here how it is declared. Compulsorily you need to use this particular keyword signed. 64-bit vector. Compute signed. I am passing the input of 64-bit vector. 64-bit vector. Vector is the name. N function. So what happens actually here is, see here, if compute underscore signed vector less than minus 1 means this is itself is a function call. This is a function call. So when this is executed, it will call this particular function. Okay, and this vector is a 64-bit vector input that you have given in your module, Verilog module. So that will be passed here. That will compute the things or some statements, keeping in the mind the sign. Sign will be kept in the mind. So think that if return value is minus 60, assume that return value is minus 60. Here minus 60 appears. So minus 60 less than minus 3. Of course true. So begin this condition gets executed. And in some cases if it returns minus 1 less than minus 3 false, it will execute, it will come out of the loop, or else it may be even positive. So sign will be given importance if you write this particular signed. Okay, so this is the signed function. So conceptually understand. Okay, so next comes full adder using task. So quickly we'll just go to it. It's a very simple code. Full adder, input a b c in, output reg sum out, intermediate sign it s1 c1 c2. See, it is looking like as if I am writing a instantiation of structural style of modeling, but it is a task. You can see here half adder is called twice. This is a task and this task is invoked here. So this task output is S and C, input is A and B. This is a half adder task. Okay, sum is equal to A XOR B, C is equal to A and ampersand B. You don't see any assign here because it is within the task and task. So this will return the half adders output here. So S1 C1 will be having half address output provided A B are the inputs of the half adder. Now this acts as a S1 acts as a one of the input, C acts as a one of the input, and we call the task same again. So A is mapped with S1, C in is mapped with B, and it will compute S and C. So S will come at sum, C will come at C2, and C out is calculated by OR gating, ORing C1 and C2. So this is a simple full adder uh, expression or full adder using task. So just show it, I'll show it here. Okay, so here I'll just execute. Meanwhile, if you have any doubts, please come up in the chat box. Okay. So it is synthesized. There are some warnings which can be ignored. So delay is ignored for synthesis. It is telling some, ignorable warnings. So let us ignore it. I think I synthesized something else. Full adder I should have used it. Check syntax. So here I should have used it. I think I clicked on some other Verilog module. So same code it is, no change at all. You can see here, same code. I have used task, and task is local to the, you can see it is local to the module. That is important. So within the module and end module, it appears. And we have called it twice. Okay. It is taking time. Yeah, it has opened. So I'll restart it. I'll just show you whether it works fine or not. So force constant, I'm giving it as 1. Some random number I give. B also 1. C in L4 set to be 0. So run it. You can see here. Sum is 0, C out is 1. Okay. So A, B and C in are your inputs, and this is how. So it will perfectly work. So just to explore that task, that it works with in the same manner how you have used your coding in the previous chapters. I want you to do it in the same manner for other things also. Let us proceed further. So count nibble. Hope you understand what's the meaning of nibble. So nibble is 4-bit vector. Half of the byte is called nibble. Now I want to count the number of ones in the 4-bit vector or in the nibble. So 4-bit vector means input is 4-bit, we call it as X. Output is also 4-bit because it to count it, so we need it can have the values from 0, 1, 2, 3. 0, 1, 2, 3. I mean 2-bit would have been sufficed. Okay, let it be. So it is 4-bit. Let us consider it to be 4-bit. Now always at X. So whenever X changes, it should execute nibble. I'm calling that particular function nibbles. N is input, X N is a output, X is a input. So this is a task I'm writing. So this is output, this is a input. So task nibbles, output is N, input is X. So integer I'm defining I in order to just have an index. Begin, I'm initializing N equal to 0. Now just here. Initially N is equal to 0, N is equal to 0. So this N, it should count the number of ones here. 0 to I less than 4 because you have only 4 bits, so maximum is 0, 1, 2, 3. That's it. So I plus plus. So x of 0 is 1. If so, increment n. If not, end it. We still you are, see, this is see, this is a for loop begin and end. So if this is a single statement inside this if, hence no begin and end is used. So this will start here, this will end here. Okay. If this is not satisfied, it will come over here. It is still in the for loop. So I is equal to 1. Now x of I is checked with 1. If it is true, nibble n will be incremented, or else again I equal to 2, I equal to 3. It will check. I equal to 4, it will fail to execute. So it will come out of the for loop and it completes the process. So this is counting the nibble. So just take this in the Verilog module. So let us, I have already written the code and kept it ready. So count nibble, check syntax. Now I explain it. Can see here. Same thing, same code. So whenever the particular index like x of 0, if it is 1, it will increment. F x of 1 is 1, it is incrementing. X of 2, if it is 0, then it will not increment, it will come out here. Okay. So it will come out here again for loop, it will continue. So this is how it will execute. Just check. So we using these concepts, we can design the questions in many ways. Very important thing here is to understand how to build the logic. Okay, I'm giving two number of ones in the input. Let us see, it should display it as 2. So you can see here it is 2. Now I force 3 number of ones, it should display. So here I'll change the radix for readability. Now I'll change it to 3 number of ones. You can see here 3. It is 3. Now if I give 4, all ones, it should declare it, it should give it as 4. It is working fine. Last check. All 0, all 0, 0 number of ones. So it is working perfectly. So this is how you need to build the logic. I hope there are no doubts. So let us go to the next one. So factorial. So what I'm doing is I am just using factorial program once again. We shall write the factorial function as well as factorial task. So in this slide we have written a factorial function. You can see a factorial function it is. In the next slide we have a factorial task. So I wanted to you to just get awareness of what are the differences here. Okay. Sorry here. Okay. Just understand here. These all things are just set up for stimulus block. Okay, don't worry much about it. It means module factorial factorial module. So n is a 4-bit vector. So means I'm giving the n values in the range 0 to 15. Okay, 3 4 5 10. This is a name I had given. Same thing I had used in recursive function, right? I was calling, so I want to display, that's why I have used a display system task. So percentage d factorial, so n also displays, factorial of n is also displayed. So here the function call happens. So when the function is called, this will execute. So it is 32-bit return value, output return value. 4-bit is a input, because if n is equal to 10, then it will have a very big number. So that's why the range is big here, integer I. So this is the same, I mean, somewhat the same logic, but in a different way. We are not using any recursive function here. Just check here. Factorial is equal to 1. Initially, I'm setting the output register with 1. For I is equal to n, n is a value that we have mapped. For example, if n is equal to 3, 3 will be mapped with this n. So n is right now 3. I greater than 0 means, so this is decrementing. So 3 decrements to 2, 2 decrements to 1. So 1 it decrements to 0. So 3 times it is going to execute. First time when it executes, factorial is equal to, factorial is already 1. 1 into, so I is 3 now. So I is 3, you will get 3. This is the first execution. Sorry. This is the first execution. Now second time. So I decrements. I is equal to 2 now. So when I is equal to 2, factorial would have been assigned with new value, that is 3. So you'll get new value. So I'll get 3 as a factorial value. I is now 2. So 2. I'll get it as 6. 6 is a new value of the factorial. So I write 6. So I would have been decremented. 1 it would have been, now I is equal to 1. Still satisfies. Factorial is 6 now. 6 into 1 is equal to 6 itself. Now again I decrements. So when I decrements, 1 becomes 0. So this will not execute. 6 is a value that is getting returned. So 6 is a value that gets returned here. 6 will be printed. So for n equal to 3, 6 is the correct answer. So this is how the function executes. Now similarly, task. In the task, what we are doing, in the function, what we are doing. In the function, we are passing only the input arguments here. We are passing only the input arguments, no output arguments are there. Because function returns a single output, and that single output is sufficient in this case. And here, whenever we declare the function name like factorial, by default, there will be something declaration happening here like this. Reg of 32-bit with, so this would have been done in the background. Okay, so that's why we are working on it. In the task it is not so. Sure, input is n, output is 32 bits, fact. So in these all things are stimulus block arrangements. I don't dig up detail here. Only thing is here what we are doing is, first we are invoking the task. So in the invoking the task, sure, factorial task name, pass the input and output argument in the order. So first order is output. So this is the output, this is the input argument. Compulsorily you need to mention the output argument also. Now we are passing it. So when we pass it, so this output is getting mapped with fact here, and the input is getting mapped with this n, and then the process carries. So think that n is equal to 3. So this n will be 3. Integer I, same thing. So initially, so output I'll also declare it as reg out. Sorry, intermediate reg out. So now what I do is reg out, I set it to 1, like in the previous case, factorial equal to 1, like that here. So for same logic, reg out, replace factorial with reg out, same logic. What we are doing is after some delay, we are assigning out equal to reg out. See, one thing is if you want to keep everything same, don't give this delay, don't have this reg underscore out, directly have out. Okay, that also works. Fine. So these are the two cases of functions and task used for the same application, that is factorial, finding the factorial. Let us have it in this code. So new source. I have a code here, factorial mod is the name. So we use a function first, Verilog module, factorial underscore mod is the name. I'll paste it. It's the same code. I'll check syntax. The name is factorial mod module. So check syntax, save it and then check syntax. So just have a check here. So it's the same code. I'm calling the function factorial. No recursive function, just executing as it is. Okay. So it is done. So simulation factorial mod. If I execute, that value will get computed by itself. So meanwhile, we'll just also analyze the the task task code that we took for the explanation. So GUI is getting opened. So here it is opening. So my concentration is here. You can check here. Factorial of 3 is 6, 4 is 24, 5 is 120, so 10 is so and so. This also is working fine. Without recursion also we can design the factorial logic, right? So now we shall go for the next one using task. Verilog module. Let me name it as stimulus. I have already copied it. Let me paste it here. I'm pasting it. Save. Stimulus, find the stimulus. Before that I check syntax. So same code here, no change at all, same code. So why it is shown is in order to convey that timing constructs are allowed in the task, whereas in functions timing constructs are not allowed. That's the meaning. Okay. Next, simulation. Yeah, you can check here 6, 24, 120, 362, 8880. So it is also working fine. Okay. So this is also working fine. Only thing is we have allowed some timing construct in order to show that in task it is allowed, but in function you cannot have this timing constraints. So that's why it has been shown here. Even if you remove this timing constraints, it will work fine as your function, same as it is. But in functions you cannot have the timing constraints. Okay. So this is all about your task and function. I hope the things are clear. I'm going a bit fast because thinking that these concepts are already well versed with you since the earlier units. So do it yourself. I'm giving you certain tasks you can try by yourself. Define a task to compute the factorial of a 4 number. The output is 32-bit value. The result is assigned to the output after a delay of 10 time minutes. I think I solved it. Just now I shown it. I did not wanted to show it, but I've shown it. So this is already done. Let it be. The same code that we just now discussed. Come to the second one. Define a task to compute even parity of the 16-bit number. We have already witnessed how to calculate the parity. So you can easily do that. But what is the change? The result is 1 bit value that we all know. So if it is even parity, then it should be 1. That's it. Okay. That is assigned to the output. So what is the change here is the result 1 bit that is assigned to the output only after the 3 positive edge of the clock. So this is the important thing. I want you to assign the output only after 3 positive edges. So hint is given, use repeat loop. So this is a task you need to carry out. Next, use the task and functions. Using task and functions, design the traffic signal control discussed in the previous unit. So in the previous unit, we had discussed traffic signal controller. There, you have an ample amount of scope in order to use a task or and or function. Okay, so you can use task, I'm giving some hint. You can use task in order to specify the delay. Had just given that task, given that work for you, homework I can say, for you to define the delays by yourself, right? So you can use the stick trick. Next, design 4-bit triple carry adder using task called full adder. Using task called full adder. So this also you are supposed to do it by yourself. Okay. So with this, we are concluding this task and functions lecture. If you have any doubt, please come up in the chat box. Meanwhile, I think I had not shown the simulation of the re-entrant task. I'll just show that re-entrant task. Okay. Re-entrant task means if task is called two places at a time. See here. What we are doing is just ignore it. It is just for displaying the things. Initial, I'm giving some actor. Here, what we are doing is A and B are the inputs. I'm doing the bitwise operations AND gate, OR gate, XOR gate. A, B are your inputs. Now in bitwise, I think we had done it, right? So we had done it. Why did I take this? Let it be. I think it has done it already. I think I have done it. Okay, sorry. So that's it. Re-entrant task, I think re-entrant task is like when you call always block, when you have to always block, call the two tasks at a time. I think I did not, I forgot it and I prepared something else. Let it be. So you can try by yourself then. Okay. So re-entrant task, I did not show the simulation. I forgot it actually. This is the re-entrant task. Yeah, this code. This code I wanted you to try. Same code. I have written the code as it is. So you use to always block, call the task at a time with the two different inputs and output sets and try it. You'll get the wrong answer. So once you click it as automatic, then you will get the right answer. So that I wanted you to try it. I think I prepared it, but somewhere I missed it, I guess. I think I missed it. Let it be. Let it be. You can try it by yourself. It definitely works. Okay. So that's it for today's session. If you have any doubts, please come up in the chat box or unmute yourself and speak. I'll address your doubts.